Welcome to True Tactical Studio. In this video, I'll guide you step by step through setting up the Modular Third-Person Framework in Unity 6.1, from importing packages to configuring advanced interactions. Let's get started. First, let's import the required packages. I'm bringing in the Modular Third-Person Framework, Unity's animation rigging, and Cinemachine for camera control. For demo animations, I'm also importing Unity's starter assets. This setup ensures all core systems are ready to go. Now let's add the ground object. I'll create a plane in the scene and assign it to the ground layer. At this stage, I'll also set up our layers: ground, interactable, and player. These layers help organize scene objects and are essential for collision detection and interaction logic throughout the framework. Let's add our player character and our virtual cameras: default, aim, crawl, swim, and dive to the scene. Next, let's set up the camera system. I'll add the camera orchestrator script and the Cinemachine brain to our main camera. This will manage camera transitions and keep gameplay perspective smooth. Next, let's set up our virtual cameras. We'll add 5 virtual cameras in the VCam section of the camera orchestrator: default, aim, crawl, swim, and dive. After creating each virtual camera in the scene, I'll drag and assign them to their respective fields here in the orchestrator. Now, I'll configure the sensitivity to control how quickly the camera rotates, as well as set the top clamp and bottom clamp values. Finally, I'll add the aim layer in the camera orchestrator. The aim layer tells the camera which objects it should interact with when determining where the player is looking or aiming. Next, I'll set up the player camera route. This is the transform the camera will follow, ensuring smooth third-person movement and alignment. I'll also set up the aim point. This defines exactly where the player is looking, so aiming and targeting are always accurate. Next, I'll attach the player core orchestrator to the player game object. All the necessary components are added automatically. After that, I'll assign the player game object to the input action and movement input handler fields in the camera orchestrator, so the camera and controls work seamlessly together. Then, I'll assign the player camera route to the tracking target field in each virtual camera. This ensures every camera smoothly follows the player's movement throughout the scene. Now let's fill in the fields inside the player core orchestrator. First, I'll assign the player configuration scriptable object, which holds all the other scriptable object assets for our player settings. Next, I'll add the input core orchestrator, movement input handler, and menu input handler to their respective fields. These handle player input for movement and menus. Then, I'll assign the camera orchestrator to connect the player with our camera system. After that, I'll add the vitality scripts, health, stamina, and breath, so the player's stats can be tracked and managed. Now I'll add both the player hand IK system and the player foot IK system for realistic limb placement. Let's also assign the animator, capsule collider, and rigid body components, which handle player animations, collisions, and physics. Next, I'll link the main camera and the aim point to their fields for proper camera tracking and aiming. Then, I'll add the aim lock rig to support advanced aiming mechanics. And finally, I'll assign the hand and foot transforms for both the right and left sides, so the system knows exactly where to position each limb during animation and IK operations. Now, I'll assign each scriptable object to its matching system: breath, stamina, and health. This step configures the player's core stats and enables all the logic for managing breath, stamina, and health automatically. Next, I'll link these 3 systems: player health, player stamina, and player breath, to the player UI orchestrator. Now, let's set up the player hand IK system. First, I'll assign the ray config and constant config scriptable objects. These hold all the parameters for hand placement and raycasting. Next, I'll add the player animator and the player collider, so the IK system can smoothly sync with player movement and detect interactions with objects. Finally, I'll assign the hand and IK target fields: right hand IK target, left hand, and left hand IK target. Now, let's configure the player foot IK system. First, I'll assign the ground layer, which the system uses to detect terrain and surfaces under the player's feet. Then, I'll add the animator, so the IK system stays perfectly in sync with the character's movement. Next, I'll assign the right foot IK target, and left foot IK target. Finally, I'll add the constant config and ray config scriptable objects, which store all the settings for precise foot placement and ray casting. Next, let's set up the rig builder. First, I'll add the aim lock rig. Then, I'll assign the hand IK rig and the foot IK rig. Now, let's finish setting up the animator. First, I'll assign the character's avatar to ensure the animations are applied correctly to the player model. Then, I'll add the animator controller. Next, let's set up the menu input handler. I'll create and assign the button that will be used to open and close the pause menu UI. This lets the player easily pause the game and access menu options at any time during gameplay. Now we'll configure the movement input handler and set up each control action in detail. Let's start with the move action. Here, I'm creating a composite action using the up, down, left, and right keys. I'll set the component type to 2D vector and the mode to digital. Choosing digital is important because, in strafe or aim states, the player can move in 8 different directions, including diagonals like up left and down right. Using digital mode ensures every direction is responsive, so movement always feels natural and precise. For the look action, I'll add 2 processors, scale vector 2 and invert vector 2. These processors let us fine-tune the camera controls, adjusting sensitivity or flipping the axes to match your preference or your game style. You'll see this setup in action around 11:20 on the timeline. Jog and sprint are set up as pass-through actions. This configuration allows both actions to register independently, so players can easily switch between different movement speeds without conflicts or missed inputs. All other inputs, jump, crouch, crawl, roll, aim, jog, and sprint, are configured as individual button actions. For demonstration, you'll notice that cover, climb, parkour, utility interact, swim exit, and dive action are the only inputs that use the same key. This is just a default setup for testing. Feel free to assign unique keys or buttons to any action as you prefer. The system is designed to detect and handle multiple actions on the same key without conflict, but also lets you fully customize your input layout for your own workflow or player preferences. But don't worry, this is just a default setup for testing. The real strength of this framework is that you can easily change any input key or button to suit your workflow. Whether you prefer every mechanic to have a unique button or want to streamline controls with multi-purpose keys, the system will adapt and detect your choices automatically, ensuring everything works without any issues. Feel free to experiment with different layouts, add gamepad buttons, remap keys, or even use UI triggers. The system's input detection logic ensures every mechanic, whether it's movement, looking around, or advanced traversal, remains fully responsive and conflict-free, no matter how you configure your inputs. Throughout this setup, I'm checking that every action is mapped properly and that the system responds just as you'd expect. Taking the time now to set up inputs carefully gives both players and developers full control and flexibility for the best gameplay experience. Now, let's set up the UI elements for the framework. First, I'll add a canvas to the scene. Next, I'll drag the Vitality bars prefab from the folder. This includes the health, stamina, and breath UI elements. I'll anchor these bars to the bottom left of the screen, but feel free to position them wherever best fits your game's design. Then, I'll add the pause menu UI, which lets players pause the game and access settings or controls at any time. After that, I'll add the controls wizard, making it easy for players to see or customize their control layout. Finally, I'll add the debug panel UI. This panel lets you inspect key flags and monitor different systems in real time while testing your game. I'll also anchor the debug panel UI to a convenient spot on the screen so it's accessible during development. Next, I'll connect the UI bars to the player UI orchestrator. I'll add the health bar UI, the stamina bar UI, and the breath bar UI to their respective fields. You'll also notice that the debug panel UI is already fully configured when you add it, there's no extra setup required. Now, let's finish setting up the controls wizard interaction. I'll add the player game object to the on-click event of the close controls wizard button. Then, I'll select the pause menu UI and assign the hide controls UI function. Next, let's finish configuring the pause menu UI. For the resume game button, I'll add the player game object and select the hide UI function, so the menu disappears and gameplay resumes when pressed. For the controls wizard button, I'll add the player game object and assign the show controls function, which opens the controls wizard for the player. On the exit game button, I'll link the player game object and set it to trigger the exit game function. This will close the application when clicked. Finally, for the close window button, I'll again assign the player game object and select hide UI, letting players easily close the pause menu window. Now, let's finish setting up the pause menu UI component on the player game object. First, I'll add the menu input handler to the pause menu UI. This allows the menu to respond to player input for opening and closing. Next, I'll assign the pause menu itself to its field, and then add the controls wizard to its field as well. Now, I'll enter play mode to test everything. You'll notice the mouse look isn't working as expected. This usually means we need to adjust our look action processors. So, I'll stop play mode and add the scale vector 2 and invert vector 2 processors to the look action. For best results, I'll uncheck invert X and check invert Y. This will make the vertical camera movement feel more natural. I'll also adjust the scale vector 2 values for both X and Y. Lower values here will make mouse movement slower and more controlled. Higher values will make the camera move faster. Now I'll test the setup again, and as you can see, everything is working as expected. The player controls, camera movement are all functioning smoothly. As you can see, there are some errors showing up in the console. These errors are related to the footstep SFX events in the animation clips provided by Unity's starter assets. If you're using these animations, you might see warnings or errors saying that a sound effect for footsteps can't be found. This just means the animation is trying to play a footstep sound that isn't included in the project by default. To fix this, I'll open the affected animation clips and remove the SFX events from the timeline. You only need to do this once for each animation that calls for a missing sound. After clearing out those events, the errors will stop appearing and your project will run without any unnecessary errors in the console. Now I'll run the scene again. As you can see, all the errors have disappeared and everything is working smoothly. This confirms that removing the unused SFX events resolves the issue. Next, I'll test the pause menu UI. At first, the menu doesn't fit the screen, so I'll quickly adjust the anchors to fix it for any resolution. Then I'll check the button, Resume, Controls Wizard, and closing the menu with the Escape key. Finally, I'll test the Exit Game button. It stops play mode in the editor and closes the application in a build. Now let's build the cover objects from scratch, so you can see how simple it is to use and configure the interaction system. First, I'll create a new object and name it High Cover. I'll assign a unique color to make it easy to spot, and set its layer to Interactable so the system recognizes it. Then, I'll add the cover object script to this object and set its type to High. Next, I'll repeat the process to create a low cover object. This time, I'll name the object Low Cover, assign it a distinct color, and set the layer to Interactable. After adding the cover object script, I'll choose the cover type as Low. Now, the player will be able to interact with both high and low cover objects in the scene. Now let's walk through creating our climbable objects from scratch, starting with a ladder. First, I'll make a new object and name it Ladder. I'll assign it to the Interactable layer and choose a unique color so climb objects are always easy to spot in the scene. This can be really helpful as your level grows. For realistic climbing, I'll add a child object that acts as the ledge at the top of the ladder. It's important to resize this ledge child so it lines up perfectly with the ladder's top. I'm also giving the ledge a different color, which helps you visualize exactly where the player will transition from climbing to standing. Next, I'll double-check the layer mask on the ledge to make sure it's set to Interactable as well. Using the correct layer masks ensures the interaction system detects the player at the right time and prevents bugs where the player can't reach the top. With the ledge child ready, I'll assign the ledge object script to it, then choose Ledge as its type. On the ladder itself, I'll add the climb object script and set the climb type to Ladder. It's also important to set the bounds on the climb object. This tells the system exactly where the climbable area is, so the transitions feel natural and reliable. Now, to create other climbables quickly, I'll duplicate the ladder object. For the wall, I'll just rename the duplicate to wall, change the climb type to wall, and check that the ledge child lines up and is set correctly. I'll repeat this for pole and rope, updating the names and climb types each time. Keeping the ledge a different color on each climbable helps during testing and makes it easy to spot issues before you even play. As you can see, this modular approach means you only need to build and configure a climb object once, then you can duplicate and customize for as many types as you need. This setup supports complex level design, lets you fine-tune how each climb behaves, and ensures the player always has a smooth, consistent experience moving from climbing to standing or running. Taking the time to set up ledges and climb types correctly up front will save you a lot of time later. Now let's build out our parkour system, step by step, so you can see exactly how flexible and modular this workflow is. First, I'll create a new object in the scene. I'll set its layer to interactable. This is essential for the interaction system to recognize it during gameplay. Next, I'll add the parkour object script to this object and select vault as its action type. Assigning a unique color here is really helpful. Not only does it make objects easier to identify visually, but it also helps you troubleshoot and organize your scene as you add more interactive elements. I'll finish up by renaming this object to vault. Having clear, descriptive names in your hierarchy is always a good habit, especially when working on larger or more complex levels. Moving on, I'll create a second object for the small jump action. This time, I'll assign its layer to ground because we want it to behave both as an interactable and as part of the environment's main collision system. I'll rename the parent to small jump and then add a child object inside, which I'll call parkour object. Adjusting the child's collider so it fully covers the parent is important. If the collider is too small or misaligned, you might run into situations where the player can't trigger the parkour action from certain angles. I'll also assign a distinct color to the child, change its layer to interactable, add the parkour object script, and set the type to small jump. Taking the time to get the collider size and layer mask just right can save you a lot of frustration during playtesting and helps ensure consistent, reliable player interactions. For the high parkour object, I'll start by creating and renaming the parent to high parkour and then add a child object, which I'll call high parkour object. In this setup, I want the collider on the child to extend on both sides of the parent, not just above it. This design makes it easier for the player to access the parkour trigger from a wider range of directions, which is crucial for larger obstacles or more open-ended environments. Again, I'll set a new color, add the parkour object script to the child, and select high jump as the type. Remember, the more you customize these colliders and trigger zones, the more fluid and fun the parkour system will feel in your game. Finally, I'll add a slide parkour object. I'll create and rename it slide parkour object, choose a bright, easily visible color, set its layer to interactable, and add the parkour object script with slide as the selected action. Throughout this whole process, don't hesitate to experiment with both object and collider sizes, colors, and naming conventions. As your scene grows, this attention to organization will make level design and debugging much easier, and if you ever need to hand off your project to another developer, they'll immediately understand what each object is for. The modular design of this system means you can quickly duplicate, rename, and retune each parkour object for new obstacles or more advanced movement options. For example, if you decide to add a diagonal vault or a longer slide, just duplicate the relevant object and tweak the collider or script settings. Playtesting different collider shapes and trigger sizes is key. Sometimes, making a collider slightly larger or offset can make a huge difference in how smooth the parkour feels for the player. With all these parkour objects set up, your player now has access to vaults, small jumps, high jumps, and slides. This unlocks a much richer gameplay experience, and gives you plenty of options for creative level design. Now let's set up the water area for our scene. First, I'll create a plain object and name it Water Object. I'll assign the layer to Interactable, then add the water volume script to this object to enable swimming and diving mechanics. Next, I'll create ledge objects and place them wherever I want the player to be able to exit the water. Each ledge gets the Interactable layer and the ledge object script, with the type set to ledge. If you don't want the ledges to be visible in-game, just uncheck the mesh renderer on each ledge object, leaving only the box collider, or any other collider you choose. This allows the system to detect interactions without cluttering your scene visually. With this setup, the player will be able to enter, swim, dive, and exit the water at the ledge points.